Our final project is drowsiness and telegating detection app design. I'm Haoying Wang.
I'm Moye.
I'm Jiahui Li.
First, I will introduce the drowsy detection part. At the user page, the user is prompted to enter the username and then click the Done button when the user finishes entering the username. If it's a new user, the user simply needs to click the Start to set up the new profile. If it is an existing user and want to create a new profile, the user can simply click the Delete button to delete the profile and then click the Start button to set up new profile. The implementation is as follows. The app stores the user's profile in the internal storage of app using new file function. The file name is the username concatenated to the real name of the file. This flow chart simply explains what I talked about earlier. The main working page works as follows. If the user has a pre-existing file, it simply loads user's profile and starts the main algorithm. If the user wants to set up a new profile, a Setup App Profile button will pop out, and the user is able to click the button to build his or her profile. In either case, the face classifier is loaded first, which is created by OpenCV using hard cascades. Once the face is detected, it will be scaled to 480 times 480. Once the user hits the Setup App Profile button, the implementation is as follows. Our app distinguishes these two scenarios by reading the state from the user page, simply setting profile state or live state. The setup new profile page works as follows. The user first is prompted to crop the left eye pupil, and then is prompted to crop the left eye, and then place an checkpoint at left eye left corner, left eye right corner, and then the user is prompted to crop the right eye pupil, and then crop the right eye, and then place a checkpoint at right eye left corner, right eye right corner. The app stores user's profile, 3 files in total, namely left eye pupil, right eye pupil, and 4 checkpoints. When the user finishes setting up his or her profile, a Start Your Journey button will pop out, and the user is able to click to start the main algorithm. The implementation is as follows. The app simply uses the callback function for drawing boxes and flow of events. The main algorithm is explained below. First, it gets the right eye region as the interest region based on the geometry of the face detected by the classifier. It then uses a dampling matching method to match the right eye pupil, where the user's right pupil profile serves as a template. The template matching method is simply done by calling the match template function. And then it gets the point with the maximum value from the result region, which is the top left point of the best matching region, shown as the blue dot here. It then uses the template matching method again to get the exact region of the pupil, where a picture of a pupil obtained online serves as a template. The exact point of the pupil is computed as the center point of the exact region of the pupil found in the last step, shown as a green plus sign, shown here. It then gets the right eye region as the interest region based on the geometry of the face. It uses the template matching method to get the exact region of the right eye, where the user's right eye profile serves as a template. The top left point of the exact region of the right eye is shown as a magenta dot here. The corner points of right eye can be obtained by superimposing the top left corner points and the corresponding checkpoints got from the setting up profile stage, shown as the orange dots here. The declaration of the drowsiness is explained below. The eye open condition is simply set as when the distance of the detected center of both pupils to the corner points of each eye are within the 1/5 and 4/5 of the width of each eye. The height differences of the centers of both pupils and all corner checkpoints are not larger than 50 pixels. If eye open condition is not met, it is declared as other state. This may include eye closed, phase not detected, or possibly failure of detection. A standard metric for measuring drowsiness is the percentage of closure of eyelid, termed as perclose, and can be represented by the percentage of time that the eye is at other state. If perclose exists a threshold, 28%, our app declares the driver is drowsy. The figure at the top shows that the driver's eye is open. This one at the bottom shows that the driver's eye is at other state. Now, my partner Wen Boye will introduce the telegating detection part. First, I have to type my username. Because this is my first time using this app, the username doesn't exist, so I have to click the start button to create my profile. As you can see, my face is first detected. It's shown as the green rectangle. My two eyes are detected based on the geometry of the face. It's the interest region of the eyes. And then I hit the set up eye profile button to set up my eye profile. First I hit done. It prompts crop left eye pupil. And then I hit done. Next I have to crop my left eye. And then I hit done. Then I put the anchor point. Basically the left point at the corner. Because it's a mirror in the camera, so the left point is on the right. And then I hit done. Then I put the right checkpoint. Then I hit done. Next, it prompts that I have to crop the right eye pupil. I hit done. And then I crop the right eye. I hit done. And then I put the left checkpoint at the left corner, and then I hit done. And then right checkpoint at the right corner, and then I hit done. After finish setting up my profile, I hit the start your journey button to start the main algorithm. As you can see, my eyes have been detected. That's it. Thank you.
Now I will introduce the tailgating detection part. Firstly, I would like to introduce the workflow of the main working page. When the user enters the main working page, the main algorithm of the vehicle detection starts, and the app will show the traffic scene from the view of the rear camera. And then a green rectangle is drawn to indicate the vehicle region. And also, the two purple lines are drawn to indicate the adjacent lanes on the left and right side. And then the following distance is computed and compared with the safe distance. If the driver is tailgating for a period, an alert will be generated to alarm the driver. And this implementation is based on these two procedures. First, by calling the onCreate, we can find the camera view by ID and set the camera view listener. And then, on calling the on-camera frame, we implement the lane vehicle detection algorithms based on the input frame and also make the corresponding computations to get the following distance. And then I would like to introduce the main algorithm. Firstly, we'll create a color frame and also a grayscale frame with a reduced size of a factor 6 to smooth the visual effect. And then we use a Gaussian filter to blur the grayscale frame. And then we use the Canyon algorithm to find the edges in the grayscale frame. Also, we will use a probabilistic Hawk transform to find the potential lane segments. And here is a figure that we get from the result of the Hawk transforms. From this figure, we can see that the right lines are extracted from the Hawk transform and we can use them to extract the desired lanes we want. And then let me introduce the lane detection algorithm. Firstly, we call the processed lane function, and then we calculate the parameters of Hawk lanes, and also the angles of the Hawk lanes. We will escape the nearly horizontal lines, because these cannot be the right lanes. And then we will classify the lane signed based on its midpoint on the part of the frame. And then we will process the size. So here is the flow chart of the processing size. Firstly, we escape lines on each side with the opposite angle, which means that they are in the wrong directions. For example, if it is the right lane, it cannot stand from the bottom left to the top right. And then we will find the lane close to the midpoint of the camera frame. And also we will find the lane with the maximum angle. Since we have two metrics, we need to pick up the best match lane with a trade-off between the distance and the angle metric. And then after finding the best match lane, we can update the status of the adjacent left and right lane. And then I will introduce the vehicle detection algorithms. In the vehicle detection, we firstly remove the old vehicle samples. And then we detect vehicles on the camera frame based on the cascade classifier that is generated using a training file. And then for each hypothetic vehicle, we determine whether it is a valid vehicle. So the procedure of determining whether it is a valid vehicle is as follows. Firstly, we find the horizontal symmetrical axis in the vehicle regions. And then we find the number of the symmetry horizontal lines of the vehicle. And also we will find the number of the nearby previous detected samples. So the valid vehicle function will return true if the vehicle satisfies the number of the horizontal line limit and also the nearby sample limit. Then we will determine whether the vehicle is a new vehicle. If it is, we just add the new vehicle into the vehicles list. If it is not, we will update the status of the old vehicles. Finally, we will remove the unknown vehicles or false vehicles from the vehicle list. So the final step is from the vehicles that we detected from the previous step. For each valid vehicle, firstly we will determine whether both of the lane segments are inside the vehicle regions. If they're not, we simply discard these vehicles. If they are, we will draw a rectangular around the vehicles. And then we can compute the following distance based on this rectangular. Based on the preceding vehicle region and pixel distance captured by the rear camera image, we can estimate the following distance by applying the pinhole camera projection. To perform this projection requires the pixel coordinates within the image of the car ahead and also the driver's car. The figures below shows the pinhole camera projection we perform. So this figure illustrates that how any road distance z in the camera view is projected to an image pixel distance d. As a result, the following distance can be computed by z1 plus minus z2 equals to 1 over d2 minus 1 over d1, and then multiplied by f, and then multiplied by h. Z1 and Z2 are the real-world distances between the smartphone and the front of the driver's car and the car immediately ahead. And D1 and D2 are the image pixel distance equivalents of Z1 and Z2. F is the rear camera focal length, and H is the smartphone mounting height. We adopt the calculation for minimum following distance according to the 3-second rule, that the driver should stay at least 3 seconds behind any vehicle that is directly in front of the driver. So finally, we achieve the tail detection part with the parameters in the OpenXC platforms. There are 2 parameters we need. Firstly is the vehicle speed, and the second is the brake status. By using the vehicle speed, our safety distance is based on the current speed of the driver's car. By using the brake status, we can check whether the driver realizes that his car is tailgating. So, just integrating the OpenXC simulator with our apps, we can finally achieve the goal of detecting the tailgating. And then Jiahui Li will introduce the flowchart of the jersey detection and the tailgating detection app.
Okay, now I will talk about the flowchart of jersey detection and the tailgating detection app. First, I will introduce this part on the PowerPoint, and then I will show you this part in a demo on our app. After we finish the jersey detection and the tailgating detection, we combine these 2 parts together. The flowchart of our app is showing above. When we open the app will first check whether the profile of user exists or not. If not, it will create a user profile first. If it is already exists, the app will go directly to the jersey detection. Generally speaking, this app will switch between the jersey detection and the tailgating detection if there is no emergency. In jersey detection activity, the app will firstly walk around 5 seconds to detect if a driver is jersey. If not, it will go directly to the tailgating detection. Otherwise, 5 more seconds are added to double check whether the driver is jersey. If again the app detects that the driver is jersey, it will trigger an alarm to warn the driver that he is jersey. Otherwise, if the driver is not jersey, it will switch to the tailgating detection. In the tailgating detection, it will be a bit more complicated. At first, the app will calculate the distance between our car and the front car. If the distance is smaller than the safe distance at specified speed, it will trigger a temporary alarm. Otherwise, both the distance larger than the safe distance and the speed lower than the safe speed will not trigger the temporary alarm. When the temporary alarm is triggered, the app will detect whether the driver pressed the brake pedal. Whatever the state of the brake, the app will still check the speed unless the speed is lower than the safe speed. The only difference is that if a driver presses the brake pedal, the temporary alarm will stop. After 20 seconds, if the car is still tailgating, the app will trigger an ultimate alarm that will not stop until the driver decided to stop it. Otherwise, which means that the car is not tailgating, it will switch to the joystick detection. Then this app will switch in these two activity. Now I will show you how does it work on our app. Okay, now I will show you how it works on our app. Since my name has already exist here, so I just type it and you can see welcome Lee, and I just type to start, it will work. And generally it will first detect my eyes. If my eyes is open, it will switch to the car detection, as you can see here. And you can see here we detect the car, and the wheel speed is lower than 80 kilometer per hour, and the distance is higher than the safety distance, so it will switch to my eye detection. We can see it again when the car is moving, we can detect the distance is changing. And now I will change the speed. If the speed become higher, and we are on the screen, you can see that it is tell me that it's tailgating. Then I press the pedal, the alarm will start. And since the speed is less than the 80 kilometer per hour, it will switch to the eye detection. But if the speed is higher than 80 kilowatt per hour, and I set the brake, but the speed is still higher than 80 kilometer per hour, it will trigger the alter alarm after 20 seconds. Just wait a minute. I took this time longer just to show how it works. As you can hear that the ultimate alarm is triggered. Then I will show you how the joystick detection works. Since now if I close my eye, 你可以说接着。
Yeah, it shows that it is detected at other state. It means like the eye open condition is not met.
Yeah, it works. It tells me that I'm drowsy since I closed my eyes for a long time. That's how our app works. Thank you.